Hi there, lovers of music and numbers. In the last video, the third video of the series, we looked at how we could display properties associated with partitions of a certain integer number. So that, for example, the properties might be the length of the partition, the number of members in the partition, the particular values, numeric values that appear in the partition, or the occurrences of these values. So we displayed these in this kind of box here. We noted that if we partition a certain number, let's say 12, we get a certain number of unique partitions, in this case 77 unique partitions, and each one of these can be permuted a differing number of times depending on the content of the permutation itself. For example, if we ask for this permutations of this series 5322, we see them on the right hand side, that there are 12 permutations of the partitions. As far as I remember, there are 2 to the power n minus 1 unique permutations of a partition. We're now going to go on and look at how we can reduce the number of these permutations of partitions in certain ways so that we find a selection which is appropriate to what we're looking for. And I have 2 strategies to recommend on how to do that. So one of the strategies that I'm suggesting is filtering the partitions and permutations according to certain criteria, so that this reduces the number of partitions or the number of permutations that actually fall, as it were, through the filter. And there are lots of filters that we can imagine. If we talk about filtering partitions as such, we could, for example, as in this example, filter by the minimum or maximum length, or both minimum and maximum length of the partition. Here, if I select, for example, for the minimum and maximum the number 7, this will mean that I'll only get partitions that are 7 items in length. And here I can, for example, filter by the maximum value of the members. So we'll say, let's take the maximum value 3, click on that. So now we're going to get partitions of 7 items that have a maximum value of 3 included in them. So let's take that and see what we get. We'll partition the number 12. And we see that the partitions we get here, if we look on the right hand side at the top, we see that there are only 3 partitions that fulfill this criteria. 222211, 322211, and 332111. And what you're seeing below that are all the permutations of those 3 partitions, which are actually, it says here, 266 different permutations of the 3 partitions in number altogether. If I took 2 as being the maximum number, then I'll just clear that. Then I only get, there's only 1 partition that fulfills those criteria, with 5 2s and 2 1s. And here are the permutations of that single partition. So how do these filters work? If we look inside, they're actually super simple. We'll see for the minimum maximum length. First of all, as it comes out of the other Bach objects, I put a Bach flat to remove the curved brackets, and then I take a length, and I'm putting out T, that's for text, so when the number is coming out of this Bach object here, it comes out as a text rather than a Bach pointer. And then we test if that length is greater or equal to the first parameter or less than or equal to the other parameter. So that's the way it will keep within the bounds of being a certain minimum and maximum. And then if those criteria are fulfilled, then this if statement outputs a bang. And this is typical of a filter, is that first of all the input here that's being tested is put into a register, and if it fulfills the criteria, then the register is banged out and then it's passed down through the chain. If it's not fulfilled, the criteria not fulfilled, then it doesn't get passed on. Let's look at this second filter, the filter by maximum value of members. Let's look inside that. Let's put it over here for a moment. Same principle. The item comes in, it's loaded into the register. I take away the curved brackets. I output it as a text, and then I check to see if the value is less than or equal to the parameter that's coming in on the right hand side. And this criteria is applied to all the items in the list that's coming in. So that's why I use a vexpr, which is able to do this operation on an entire list. Then, in order to check that all the items fulfill the criteria, I add up the ones that come out of here, which come out, we get as many ones as items that fulfill the criteria. If the sum of these ones is equal to the length of the string, then we know that it's all ones and all those items fulfill the criteria. Otherwise, we don't get the bang out here, and we don't pass the item through the filter. So those are two filters, pretty typical how those filters work. And then as it comes out of here, I again take the curly brackets off, and I do the permutations of the partitions that fall through here. Now if I wanted to filter the permutations, it would be quite likely that I would be filtering the permutations on different criteria, because obviously there are certain criteria that relate to partitions and there's certain criteria that relate to the permutations of those partitions. For example, I can put can pop into here in between a filter that will check to see if these permutations that we are taking, if they are palindromes. That's to say, they read backwards and forwards in the same way. And if we quickly look inside how that works, we see we put the item that's coming in into the register again, so that if it fulfills the criteria, it can be output. It's reversed, the output. You check whether the reversed version of it is the same as the original version, and then if it is, if this produces a 1, it's a truth test. So if the truth test produces a 1, then this outputs a bang, and then the permutation is passed through. Let's see, for example, how many of these permutations with the existing criteria come out as palindromes. So the partition we were permuting was 222211, and we have three permutations that fulfill the criterion of being palindromes. Here they are on the right hand side. So we can then check out what these three look like as notation. Or okay, so there they go. Three different palindromes. So there are actually very few that fulfill the criteria. Let's take a little bit of a wider search here and say, well, okay, we're going to take partitions of length 7, but we'll add the possibility of there being a minor third involved, and see how many fulfill the palindrome condition. Okay, let's have a quick look now at what kind of filters we can imagine. This is just a small selection of possible filters. Filters for the palindrome I mentioned was for the permutations, but here are the filters for the partitions themselves. Filter by min-max length, we looked at that. Filter by minimum value of members. Filter by maximum value of members. We can filter by containing only these members, but that means containing these members, but other members can be contained in it. But here is a function that says contains only these members. So you can have this illustrates how certain searches can be exclusive searches, that the conditions have to be fulfilled, or the conditions have to be fulfilled, but other conditions can exist. Let's look at the other strategy that I'm suggesting for searching partitions and permutations of partitions. The second strategy I'm suggesting is property indexing. If we do a search on the basis of indexing, then we can put a Boolean operator on the output, and thereby we can make more sophisticated searches which kind of combine various conditions. Here's an example of a Boolean search operation. Again, I'm partitioning the number 12, and here I'm doing an example of indexing by the minimum and maximum length, like I did the filter with the minimum and maximum length, but this time I'm taking the indices of the partitions that fulfill these criteria. So I'm just generating a list of numbers which are the indices of those partitions. Remember that the number 12 had 77 unique partitions, and these are the partitions that fulfill this criteria: minimum 3 and maximum 4. If we do a little change to this and we say that we take the minimum maximum are 3, and then we do the search again, we see that there are fewer partitions that fulfill this criteria. If we again widen the search and say, okay, between 3 and 6 items in the partition, then we get a longer list, and so on. What we get here, I'll put it back the way it was before. Do it again. This is the way it was at the beginning. Let's look what happens once we've got this list of indices of the partitions that fulfill the criteria. Then we take the unary complement of this list. So we find out, after partition, we find out how many partitions have been generated. We know that that's 77. And then we remove from the list of 77 these particular items that have been shown to fulfill the criterion. This gives us the unary complement. So this is a kind of a Boolean negative. Let's have a look inside these functions to see how they differ from the previous example. The previous example we were filtering, in this case we're indexing. So how does that work? Well, first of all, we bring the index in that's generated by this USI. USI generates the indices on its right hand side output. The index, which is from 1 to 77 in this case, is coming in here. It's stored into this integer, and if the criteria are fulfilled, then, and the bang comes out of this condition, then that index will be passed. So whereas previously we were putting the actual partition itself into a register and outputting that, here we're only taking the index of the partition and outputting that. Otherwise the function is the same. We check to see if it fulfills the criteria. If it does, then it bang, and out goes the index. In order to do the unary complement, we need to know the maximum number of partitions that's coming in. It comes in on the right hand side, and then we pass the list of indices that have fulfilled the criterion into this left hand side. The list goes into ZL filter, which is able to remove those items from the arithmetic series that's generated on the basis of this maximum number. Let's have a look at how we can do a more complicated search based on more than one criterion. I've chosen to generate the properties of the partitions as I did in the previous video, which is to generate basically all the partition properties at one time. Here it generates the occurrences, the members, the number of members, the length, and finally the greatest common divisor. So here I'm going to do a search which says that I'm looking for all the partitions of a certain length. In this case I've put here the length from 3 items to 4 items, and all of those that fulfill the criterion of having a greater common divisor than 1. Because I'm doing Boolean operations, I have to have a little bit more sophistication in the choice of how I use them. Here I've put, following the test of the criteria, the truth test, here I've got a couple of switches on each side. One, it says that I'll switch this particular criterion on, so let's switch the criterion on. So I can switch the criterion on or off. The other switch is, do I use the criterion or do I use the unary complement of the criterion? So at the moment we'll leave it that we say that we use the criterion, and we'll try and see what happens later if we use the unary complement of these criteria. So let's take the partition of 12 and see what fulfills these criteria. So these are the indices that fulfill the criteria for the partition being either 3 or 4 items in length. This are the items that fill the criteria of having a greater common divisor larger than 1. And this, when we put through a Boolean AND, which is this ZL sect, between this list and this list, we get a smaller list that fulfills both these criteria. And so the end of the result of the query that comes out of here fulfills both those criteria. How do we then get to see the results of our query? So here's a little function here that'll return the result of the query when we click on this list, and it shows us that in this case the partitions that fulfill these criteria, that are not between 3 and 4 and are greater common divisor greater than 1. There are no 1s, and the smallest number here is 2, and they're all divisible by 2, by 2, by 2, divisible by 3, divisible by 4, divisible by 2, 3, and 6, and so on. Down on the bottom right hand side here, I've put down the Boolean list operators that are possible to use under these circumstances. First of all, these are the ZL versions. We have ZL sect, which is a Boolean AND, ZL union, which is the Boolean OR, ZL filter, which is the Boolean complement, and ZL unique, which is the Boolean XOR operator. And here we've got the same operators in the Bach versions: Bach union, Bach diff, Bach intersection, that's the equivalent of sect, and Bach symmetric difference, which is the equivalent of ZL unique. So depending if you're working in the ZL domain or working in the Bach domain, these are the operators that you can use to do these Boolean operations. So bye for now. Next time we'll go and look at how to generate transitions in permutations and make comparisons between different permutations on the basis of these transitions.